Why is a 1,3-cis disubstituted cyclohexane more stable than its trans isomer? Okay, so when we talk about stability of cyclohexanes, we always talk about the chair form. So let's draw a chair form here. And 1,3, so it doesn't matter where we start. Let's just start numbering right here. 1, 2, 3. I'll move my 1 there a little bit. So this is carbon 1, 2, 3, 4, 5, 6. Okay, so 1, 3, and we're talking about cis here. So let's look at cis 1, 3, and I'll just put one methyl group. And this says disubstituted. It can be substituted with anything, but let's just, in fact, why don't we just call it R here? And we'll put arbitrarily, we could have done it anyway, but let's just put R down. So we put R down in 1. And we're making the cis isomer here. So let's make the cis isomer first. And that means that in the 3 position, so I'm going to put my axial positions in first. So up, up, and up here. And we've got down, down, and down here. So where the arrows, or where the carbons of the cyclohexane ring point down, that's where the axial positions point down. And where the arrow of essentially the arrow that's made by the carbon-carbon bond here, where that's pointing up, the axial is pointing up. So that's how these go. And actually, this methyl group is in back there at carbon 3. So make that a little bit more clear. And now we can put the equatorial substituents in. So let's put, these are both hydrogens, and the equatorial position there, the equatorial there, equatorial, and equatorial. So these are all hydrogens, except for the R group at position 3, and so that's another R group. So this is cis substituted. So 1, 2, 3, cis 1, 3. So this tells us that it's a 1, 3 disubstituted cyclohexane. So at 1 and 3, the R groups are both down. That's indicating that they're cis. They're both on the same side. Cis means same. So they're both on the same side of the ring. If you think about the ring as being roughly a plane, the 2 R groups are on the same side. Now, this doesn't look very stable because the R groups are both axial. But if we do a chair flip, so let's just draw the equilibrium arrows and flip the chair. So that means we flip carbon 1 up. And here's our flipped chair now. Carbon 1 we flipped up so that now the hydrogen is in the axial position and the R group is in the equatorial position. So there's our R group at carbon 1. And now I'll just number these around the ring again. 1, 2, 3, 4, 5, and 6. So we have carbon 1 taken care of. Now at 3, whatever is in the chair flip, whatever was equatorial becomes axial, and whatever was axial becomes equatorial. So on carbon 3 here, the hydrogen was equatorial, so it becomes axial, and the axial is pointing up on carbon 3. Therefore, the R group becomes equatorial. So notice that after we flip the chair, both R groups are equatorial, which means that this equilibrium lies far to the right and just a little bit to the left, because this is much more stable. I'll say much more stable than the other ring flip form. So let's draw the trans 1, 3. Die substituted. That was a pretty bad chair. I'm going to just start over here. So if we start at carbon 1, and why don't I just make our R group again, just for the sake of consistency, I'll just put the R group going down again. But since this one is trans, we're going to make the trans form here. This is 1, this is carbon 1, so again, carbon 2, carbon 3 is here. So since it's trans, that means that the R group at carbon 3 is actually is up, and the R group on 1 is down, the R group on 3 is up, and up is equatorial. So here's the R, and I'll put that, since I'm making my equatorial substituents yellow, I'll put the R group here in yellow, and I'll put the hydrogen going down in the axial position. So when we flip our chair, we see that, so we're going to flip the chair so that carbon 1 is up now, and this is 2, 3, 4, so there's 1 and 4. Carbon 1 went up and 4 went down. So that means that the hydrogen here at 1 is up. The R is still down, but now the hydrogen was equatorial, now it's axial. The R group was axial, now it's equatorial. Since they're trans at the 1 and 3 position, and I should have changed this to, I guess since the hydrogens, this hydrogen was yellow here, so now it's, I'm going to keep the color in the other flipped form. The R group, so the R group was yellow there, and the hydrogen was white on carbon 3. So notice when we do these two chair forms, for the trans molecule, you have one axial and one equatorial substituent in this chair form, and you have an axial and an equatorial substituent in the other chair form. So these actually have the same stability. So this really is a 50%, 50-50 equilibrium, assuming that R is the same. So if R is the same here between these two, between the 1 and the 3 carbon, these two chair forms have the same stability. So there's our 3 carbon there. So what this means, comparing the cis and the trans, since the cis form can adopt a conformation in which both R groups are equatorial and the trans form cannot, both of these chair forms have an axial substituent. So you can't get away from that in the trans form, whereas in the cis form, both R groups can be equatorial. Therefore, the cis is more stable than the trans.